Okay, this lesson is going to be on the ANOVA. This is just a chapter summary, so hopefully you've read through much of the book. I know it can get a little computationally intense, particularly for this lesson. So we'll do one of these by hand, then I'm going to show you how to use StatCrunch to go through this. So why even use an ANOVA? So we use a two-sample t-test in the last lesson when comparing two groups. So if we had like an online versus on-campus final exam scores, miles per gallon between automatic and manual transmissions, maybe the average IQ scores between males and females. But what if we wanted to compare three or more groups, so more than two groups? What do, like, for example, online versus on campus, and we have a third one. Maybe we have a hybrid class we want to compare. Maybe miles per gallon between automatic, manual, and hybrid transmissions. Are there differences in average GPA by grade level? So here we have four groups: freshman, sophomore, junior, senior. Average height of females by continent. You know, there are 6 or 7 continents we got. Really no one lives, so to speak, on Antarctica, I don't believe. So the main 6 continents here. So we use an ANOVA to determine if there's a difference between the groups. So we cannot run, well, you can, but it would really bump up your error for type 1. So we can't run multiple t-tests. It's tempting to do that. Just run, like if you had 3 groups, you could run online versus on campus, compare those, then online versus hybrid, and then on campus versus hybrid, and look and see if there are differences. The problem is that this is going to increase the type 1 error rate. And the book kind of goes into that. In fact, there's a formula that you can actually determine this error rate. It's 1 minus 0.95 to the n, where n is the number of comparisons. And you can tell this really does bump up the error significantly once you get, particularly once you get more than 4 or 5 groups. Which is often the case when you're using an ANOVA. So I want to start off with an example. I say by hand. We're going to be using calculator to do most of the computation, and all these computations are very easy. All it is adding, subtracting, squaring, and summing things up. So the computations themselves are not hard. What's hard is that there's so many of them. It is hard to keep track of. So we're going to break it down. So at the end, you're going to see an ANOVA table, and we'll see where those values compare. But I want you to see what the ANOVA table is composed of. So suppose a professor wants to compare the final exam scores if they differ among 3 different types of courses. So we have online versus on campus versus hybrid. So I've given you a list of scores here. I completely made these up. And so the HO would be there is no significant difference in mean final exam scores between the 3 different types of delivery methods. So another way to write that is that mu1 equals mu2 equals mu3. Or we could say mu online equals mu on campus equals mu hybrid. And then the HA is there's at least 1 difference, or there are at least 2 that differ. Sort of depends on how you want to think about that. So it's not that they're all different. It's that if just one of them is different from the group, then we can make a conclusion that there is a difference. Okay, that's all we're testing here. So step 1. And I'm going to tell you what to do first, then I'll kind of show you the formula, and we'll see how all these pieces fit. It's going to be a lot, but it's going to hang in there. You don't have to write all this stuff down. You can if you want, and we're not going to be doing these by hand. I'm not going to expect you to do these by hand, but it's good to see where these pieces come from. Okay, so first we're just going to sum these scores up. And a lot of this you'll recognize from maybe even doing standard deviation by hand, or even some of the t-tests that we did a little bit those by hand. So we just sum those up. And so the online, we get 491. On campus, we get 465, and hybrid, we get 511. And now we're going to square the scores. Okay, so I went ahead and did that for you. So I squared 72, for instance, and got 5184. Squared 86, got 7396. And I did all this in Excel, to be honest with you. So I didn't do these individually. We square those up. And now we're going to sum these squares. Okay, so I'm summing these squares up within each group. And then we're going to find the mean of each group. So you just add them up and divide the way you normally find the mean. So I've already seen that I have a difference between these scores, right? So the online has a mean of 81.83, on campus is 77.5, and hybrid is 85.17. So I see I have a difference between the groups. The question is that statistically different or not? Are these differences, which is the between group variation, relatively large compared to the within group variation? So make sure you kind of see that. We have a visual here, and so we have a hybrid, and online looks like they are doing better than the on campus, but there's so much variability there. We want to know how likely is that a result that extreme to happen by chance. So the step 5 is we're going to find the overall mean. We're going to need that for the formula. So the overall mean, just add up all, what do we have, 6, 12, 18. We have 18 scores. Add them all up and divide by 18. You get 81.5. Okay, so I just went ahead and summarized all of those results in a nice little table here, right? So I have the sum of the x's, 491 for the online, the sum of the x squares, 40, 365 for the online, and then the mean for each of these values. And then the mean t is the total mean. Okay, so I just summarized this in a table just to keep me organized and so you can see where these values come in. So what is our test statistic here? So we're going to look at the f. This is simply the ratio. This is the mean squares between divided by the mean squares within. And as the mean squares between gets large relative to the within variation, we're going to see some statistical significance, okay? And there's a table we can use to do that. In reality, though, we're going to look at the p-value. It's already kind of done for us, but I'm going to show you where all these values come from. So what is the mean squares between? How do I find that? It's the sum of the squares between divided by the degrees of freedom. And we've seen degrees of freedom before. And similarly, the mean squares within is the sum of the squares within divided by its degrees of freedom. And we have formulas for each one of these. So again, we'll look at this in a second, but the total sum squares total, is just the between sum squares plus the within sum squares. We'll use that simply in a minute. Okay, so just trust me on this one. This is not a formula you're going to have to know. And don't even worry where it derives from, sort of beyond the scope of the class. So the sum squares total is the sum of the squares minus n, the total number of observations we have, it's 18 in this case, times the mean, which is 81.5 squared. So what's that going to look like? I'm just going to add them up. I've already added up all the squares, right? So I'm going to add up each of those squares. So we have the 40365 plus 307 plus 43609. Subtract out 18 times 81.5 squared. Just use a calculator for this. We get 720.5. So we're going to need that value here in a moment. So now I'm going to find the sum of the squares between. And there's a formula for that. Again, we're not going to derive this for you. Just sort of accept it on faith. I haven't steered you wrong so far, right? So accept this. So it's just the nk times the mean k minus the mean. So the mean of each group. And then we're going to sum all those up. So we take each group. So we have 6 in the first group times 81.83 was that's mean minus 81.5. Then square it. And then they go to the next group. There's 6 in that group times its mean, 77.5 minus 81.5, and then square that, and so on. And I just use a calculator, crunch that out, and I get 177.46 when I add all that up. So notice what we have here. We have a formula already over here. The sum squares total is the sum of the squares between plus sum of the squares within. Well, I have 2 of those now. I have the total, which is 720.5, and I have the between. I can just plug those in and solve using some algebra skills. Just subtract 177.46 from both sides, and I'll have my sum squares within, 543.04. This is a lot coming at you, I know. But all this is just arithmetic, right? It's sort of hard to know where these pieces come. Notice what I'm waiting for here. So now I think I have everything, right? Oh, I need my degrees of freedom. So my degrees of freedom within is n minus k. So n is the total number that I have minus k are the number of groups. So I have 18 minus 3, which is 15. And now the degrees of freedom from between is just k minus 1. So the number of groups, k is the number of groups minus 1. So 3 minus 1 is 2. Okay, so I plug those in. And so I have 177.46, which is the SSB, over DFB, which is 2, and I get 88.73. And then the sum of the squares within is 543.04, divided by its DF, degrees of freedom, which is 15, and I get 36.20. And now I'm just going to divide those two. So let's come over here just to give myself some room. So the mean squares between divided by mean squares within is the 88.73 divided by 36.20 equals 2.45. That is F. I know this is a lot at you. And the good news is that you're not going to have to do this this way at all, but I want you to see where these numbers come from. So, but in this example, we have our f equals 2.45. I use the f calculator or the ANOVA calculator for the f distribution on StatCrunch. And so there's my 2.45, but look at where's my critical value here. So I look over here at the denominator df, which is at 15, so I go to the table. This is in the back of the book. Here we go. So now at numerator degrees of freedom is at 2, and we look at that intersection, we look at 3.68. That's the value I'm trying to beat. I'm trying to get bigger than that if I wanted to reject HO, but it's not bigger than that. So my f is not big enough here at the 0.05 level of significance. So since the p-value of 0.12 is higher than alpha, we fail to reject HO. There's not enough evidence to conclude that there is a difference among the 3 different types of classes. And we saw that a difference was there in my small sample, but we know through sampling variability that could happen by chance. And so 12% of the time, I would get a difference that extreme. So I fail to reject. That's not small enough. So what would this look like in StatCrunch? Well, much easier, of course. So we go to Stat, ANOVA, one way. And so you're going to select the columns, online, on campus, and hybrid. And then you're going to get your ANOVA table. And it's going to go ahead and give you some of the summary statistics that we've computed before. It's nice to see them there. And then there's our ANOVA table down there at the bottom, right? And so we see our p-value of 0.12. Notice that's exactly the same we got when we used the def calculator. Let me go back here real quick. See the 0.12? That's the p-value. In our f statistic, 2.45 if I rounded it. So all of these values, these may look familiar. Let's look at this table within our computation. So look at df. So the column df is that degrees of freedom between. Notice the 2 and the 2. Error and df. We have 15. That's the degrees of freedom within. And sometimes you'll see slightly different notation in different books. In fact, our book may use a slightly different notation with these. The sum of the squares between 177, I got 0.46. The table, the computation StatCrunch, 177.33, just some rounding error. We got 543.1667, and when I did this by hand, I got 543.04. Again, that's pretty close. Our total, sum of squares total, 720.5, that is the same. Our MS for the column, 88.73 is what I got. Our ANOVA table, 88.6666. Similar for mean squares within, that's that error. The mean squares error, 36.2. And then our F statistic, 2.45. And then we have our p-value here at 0.12, which we saw that we obtained earlier. So now let's look at an example. And all we're going to do, I'm not going to show you the calculations by hand, but I want you to sort of be thinking about that as we go through this. Suppose a teacher is testing multiple reading programs to determine the impact on student achievement. There are 5 different reading programs, and her 31 students are randomly assigned to one of the 5 programs. The mean achievement scores and variances for the groups are recorded along with the means and variances for all the subjects combined. So we can state our null hypothesis. The mean scores are the same, or there is no difference in the mean scores. There are a couple different ways to word this, and then symbolically, mu1 equals mu2 equals mu3 equals mu4 equals mu5. And then HA, the mean scores of the 5 methods are not the same. Or another way to read that is that there's at least one difference, or there are at least 2 that differ. Again, there's not an exact way to write that, but something of that nature. Another way, there is not a significant difference in the reading methods. There is a significant difference in the reading methods. Another way to word that. Now notice this is not for HA. That's not mu1 is not equal to mu2, which is not equal to mu3, which is not equal to mu4, which is not equal to mu5. They don't all have to be different, as I mentioned in the first example. Just so long as one of them, if one of them is different than the other ones, that's where I would reject HO. So here is the data for method 1, 2, 3, 4, and 5. Notice they don't have to have the same number in each. Computationally, it's easier if they do, but since we're using the computer, it doesn't really bother us that much, right? Okay, so I'm going to first whenever I'm going to run or think about running ANOVA or comparing, I always run summary statistics and create at least one visual. So I had ran in some summary statistics. I'm looking at the means and medians, looking at the standard deviations, and I run some box plots. So there are a lot of assumptions that kind of come packed in with ANOVAs. Normal distribution. The variances need to be somewhat the same. They don't be exactly the same, but close. We can't have some that are just huge relative to others that have no variation. Okay, so just from looking at this, if we're just kind of using our gut, right? Method 1 versus method 5, there definitely appears to be some differences there, right? There's not even an overlap between the scores. So I'm pretty confident there's going to be a difference between method 1 and probably 4 and 5. Between those, and maybe even between method 2 and 4 and 5. Between method 2 and method 5, maybe. We'll see. So I'm going to run ANOVA to determine this. How likely is it that we can get a difference by chance? So go to Stat, ANOVA one way. It does give me some summary statistics, but again, I like looking at that beforehand. And you can choose when you're running the ANOVA to create some visuals along with it. I generally do that first, and I'll even do some afterwards. Sometimes it gives me something a little bit different, another different perspective on it. And we look down here at our p-value, 0.0001, pretty low. It's a pretty big F statistic too, right? And that's where we would have gotten that is this MS, the 37.62, divided by the 3.363. Okay, so let's just blow this up a little bit. And so we always need to make a conclusion. We got a low p-value. We're going to reject HO. The mean scores of the 5 methods are not the same. There's at least one difference. So a natural follow-up question, right? When we do reject HO, we say they're not the same. Well, which ones are different? So we need to run what's called a post-hoc test. Now, often before we even run the ANOVA, we may have a suspicion that one is going to be different than the other. We can do something called a planned contrast. We're not going to get into that in this class, but just know you can plan that ahead of time. Here we're going to run a post-hoc test. Now there are at least 18 of them. If you go into SPSS, which is a much more robust program than we're using a free version StatCrunch that comes built in with your textbook and does most of that we need. It just has one. It has the 2 key. StatCrunch just has one, so that's the only one we're going to run here. So I go ahead and go back into the one-way ANOVA. I select it, and I go ahead and run the post-hoc test. In fact, when I'm running the ANOVA to begin with, if I kind of see there's going to be a difference, I'll go ahead and just click that button. And now I see some differences. Let's pull this box plot back up, and let's see how to read this. So we have method 1. So we're comparing method 1 to method 2, 3, 4, and 5. And method 1, we see there are some significant differences between method 1 and method 3, 4, and 5. And that sort of makes sense visually, right? There's not a statistically significant difference between method 1 and method 2. Its p-value is greater than 0.05. Let's go on to method 2. So method 2, it only differs from one of these. So method 2 and method 5, there's a statistically significant difference between those two. And then method 3 only has one value. So method 3 and method 5 have a difference. So this is a very common way that these are presented in these post-hoc tests. Method 4, there are no differences between method 4 and method 5. So those are the last two that I had to compare. Example 3. Suppose a professor was interested in determining if there was a relationship between student GPA and seating choice in the classroom. Okay, so the data are often presented like we've seen in the last couple examples where I have front, middle, and back, and I'm collected the data. But often it's given in just 2 columns, and all of my variables are sort of labeled in that way. So notice how these 2 data sets are exactly the same. So here I just have one column called GPA, and then I have a column that tells me the attribute of that particular variable. This is actually the more common way you'll see if you take another course in statistics. Or if you are going to be using SPSS, this is how it really likes its data to be put. And StatCrunch can analyze the data that way. Okay, so let's state our HO and HA. So HO, there is no difference in mean GPA among different seating. Another way we can write that is mu1 equals mu2 equals mu3. Now, I typically prefer to write this using subscripts that make sense to me. So mu sub f equals mu sub m equals mu sub b. But so for front, middle, and back, certainly up to you how you write that. And HA, there is a difference in mean GPA among the different seating groups, or there's at least one of the means is different, or at least two means differ. Okay, so we're going to run some summary statistics. Kind of glance down at the means. Appears to be a difference for me anyway, just kind of my gut. Looks like the front and the back. I mean, we're going from a 3.45 GPA to a 2.81 GPA. That seems like it's going to be a difference between that. Looking at the medians as well. Let's look at a box plot of this. Well, there's a lot of variability sort of within the front, right, and the middle. Not quite as much in the back. So hard to know. There's a lot of overlap there between the front and the back, right? So maybe there's not enough to detect a difference. Let's see. So I'm going to do the ANOVA one way. Select the columns, front, middle, back. Again, if it were given to you in single columns, you would just select that value and select responses in one column and then the factors, which is the row in this case, in the second column. And I'm going to go ahead and anticipate that there's going to be a difference, so I'm going to go ahead and click that option to compute the Tukey HSD at the 95% level. We run it, and what do we got here? So again, we see our summary statistics, and then there's our ANOVA table. And I come down there and look at the p-value, 0.0026. Means I can reject HO. And so since p-value is less than 0.05, we can reject HO. Conclude there is a difference in mean GPA among the different seating, front, middle, and back. So when you're reporting these statistics in a research paper, you always give the test statistic and the p-value. So either you have to give the test, you don't have to, but it's appropriate to give the test statistic. And if you're not going to give the exact p-value, then at least say it's less than 0.05. Okay, you'll see in both ways in research articles, but you'll almost always see an ANOVA table or at least the test statistic, the F statistic given. And so here's our Tukey HSD. So which ones differ? So the front is different, statistically different from the middle and the back, below 0.05. The middle is not different from the back. Okay, so the only differences are the front has a higher GPA than the middle, and the front has a higher GPA than the back. Okay, so from the post-hoc test, we conclude those who sit in the front have a statistically higher GPA than those who sit in the middle or the back. So I hope that makes sense. ANOVAs, we use ANOVAs again when we are comparing more than two means.